say this CP and CPK stuff is all well and good, but what do I do once I actually collect the data? And I realize that my process is not capable. Well, there are several courses of action. Also, where else can I use this process capability analysis? The next thing we want to ask are, what are the characteristics that we need to measure within the process capability study? What should they look like? Well, they should be key factors in the quality of the product or process. They should be adjustable values. And we want to do this within a controlled atmosphere. If there are outside factors that are influencing our data, then our data will not be telling us what it needs to. So, I mentioned earlier that the customer defines the specification limits, but who else can do that? Well, we could go to industry standards or the engineering department that converts the voice of the customer into customer requirements. Having specification limits clearly defined and agreed to is a key point early on in determining process capability. You can see here, anything outside of those specification limits is going to be a rejection. Anything within those specification limits is accepted. That's why these things need to be very well clearly established and agreed to. When we're converting those standard deviations into Z values, what we want to do is have a common knowledge. That's the reason that we do it. So that Z transformation. How do I convert my data using mu and sigma into zeros and ones with the Z distribution? Well, you can see the equation there for a Z transformation. Once we do that Z transformation, we can apply the rules of the Z distribution or the standard normal curve using the Z table or standard normal table. The way that this table works is the Z values are on the outside edges. The first decimal place of a Z value is going to be on the y-axis or the up and down along the left side, and then the second decimal point of a Z value is going to be across the top. If I'm looking for a certain type of Z value, I simply start going down until I reach the first decimal point that I need, and then go across to the second decimal point that I need in a matrix style. Everything inside of the table is considered the probability or area under the curve. Many of the Z tables have a drawing like this that describes the area under the curve. You can see the equation may be a little overwhelming, but all we're talking about is what is the percentage of shaded area under the curve. You can see here, if we go to a positive 1.5 Z value, starting at the far left side, what is that area that is covered under the curve? Using this equation, you can see that it's 93%, or 0.933. Another example, because the standard normal curve is symmetrical, and we know that the area under the curve is a total of 1, we can work backwards into these percentages. You can see here that if I go to a Z value of 0.126, but I want to know what's left, we can just subtract the total from 1 and we get 10%. A third way that we can use the z-table and z-distribution is to determine what is the difference from one z-value to another z-value. In this particular example, you can see that I'm trying to find the area under the curve between negative 1.25 and 0.37. So, using the z-table, I know that I can determine what it is up until 0.37 and what it is up until 1.25. If I subtract the negative 1.25 area under the curve from the positive 0.37, I end up with the area under the curve between those two z-values, which ends up being 53.9%. When we talk about nonconformance, again, that yield is inside of my upper and lower specification limits. My target value is obviously going to be in the middle of that specification range. This is one way that I can predict what my process yield or probability of defects is going to be using the z-table. Here are the equations to apply that, and the function within Excel that you can use to do this automatically. The 1.5 sigma shift is a theory that is applied to Six Sigma that is used in the change of variation over time. So when we talk about long-term process capability, there's going to be a 1.5 sigma shift that occurs over time. Here is short-term versus long-term z-scores and the specification limits to that. So remember that your data must be normal in order to calculate a proper CPK or PPK. Normality test, you can see here, is your data against the normal line. In a later session, we'll get into what the p-value means and how we can use that. In Excel, this is the equation or function that you can use to include that 1.5 sigma shift. Remember, for short term, we do not include that because it is a theory over the long term of the process. We've been talking this whole time about variable data and how we use variable data for process capability. We can do the same thing with attribute and discrete data. We use control charts or run charts that are associated with attribute data. One way to easily recognize attribute data control charts is that they are all letters: P, NP, C, and U, versus statistical terms like X bar, R, and S. One of the distributions that we can use for attribute capability is binomial. You can see here how we get that binomial on the left of the slide using Minitab. The output of that Minitab function is on the right. We are using a p-chart to do this. The other way that we can do this for certain types of data is using the Poisson capability analysis or Poisson distribution. This is where we use the U-chart. And this is how we get it in Minitab. This is what comes out of Minitab. It looks very similar to the binomial, but again, it's all based on the data that you have. Stability is a major concept within Six Sigma because it is how the process performs over time. We want to make sure that it is predictable over time and not out of control. There are two types of variation that will cause a process to perform out of control: common causes and special causes. Common causes are that natural flux of variation that always exists. Special causes are something that is assignable, something special out of the ordinary.